Hey, welcome back. So I thought I would talk a little bit about the Commodore 64 again, the power supply. So, because lately there has been some interesting development by Ilker from Turkey. And he has made a power supply which basically uses a standard generic 5 volt 2 amperes USB charger, USB cable, a DIN plug, and here is the really cool thing he has done. So you may have heard before that the Commodore 64 has a voltage doubler. So like here, for example, this is the voltage doubler. The AC comes in here, this one charges up, and when the polarity changes, this charge is dumped in, so you get a double voltage here. Mr. Ilker has, sorry if I pronounce it incorrectly, but he has thought this through quite different, and I like it very much. Instead of using the Commodore 64 voltage doubler, which needs an AC or a alternating current, he's using a voltage doubler himself to get the 5 volt up to 10 volt DC. He states that it's only for the Commodore 64C right here, right? So, sorry for checking. And also the Max 660 voltage doubler IC is using is 100 milliamps. So this is the input of the Commodore 64 power supply, and basically I have ground here. 3 pins are ground, only one is used though, and then you have 5 volt on the switch, and then you have 9 volt AC here coming in. One of them is switched, and the one which is switched goes up to the voltage doubler, and might look a bit scary, but it's actually quite easy. What happens is that you have a rectifier, that means, and then you have 9 volt or so here, which is said to be unregulated. And then this 9 volt will also sit here. So if the voltage on this side goes below 8 volts, which is like the dial drop here, then this capacitor will start to charge. So the voltage goes down and down and down and down and down, and the voltage over this capacitor will then go up and up and up and up and up. And I'm not talking about voltage reference to ground, I'm just talking the voltage over it. So now what happens when the polarity changes? Well, the charge that was here will now be pushed. It can't be pushed this way because this one is stopping current from going this way, so it will push it in here. So when this voltage goes all the way to like 12 volt amplitude or something there, or maybe higher, then the 12 volt or so, maybe 11 volt that was over here, will then be pushed together with the 12 volt in here, minus the voltage drop here, of course. So you get a voltage here which is between 18 or 24, I think, such that you can drive the 12 volt regulator, because you need more than 12 volt. So that's quite easy how that works. And the thing is that these new power supplies, they don't provide proper sine wave. So, and also they are not floating, and what that means is if they're not floating, they are a reference to ground, and therefore this point and this point is the same. That's one thing, and the other thing is that you can get ground loops. So, but still there's something that puzzles me. How is this 9 volt reference to ground? You know, the question that always comes up with these power supplies is, how do they drive the 50 or 60 hertz generator that drives the time of day? These usually don't work with these new designs, which are non-isolated. So, and to remedy that, I need to understand how this works. So I have done some simulations, we can have a look at that later. And now we're talking about the original power supply. So, but what you see here is that you have a path down to ground here. So, the one from Retro Game Supply. It has like a push-pull configuration, and it basically grounds. Let's go back to the schematics. So this is how it works. So what it does, it grounds this one, and the reason why it doesn't ground this one is because if you ground this one, then when this switch it off, then he's absolutely sure that there's no power going on when the switch is off. So that's one concern. The input here gets a 12 volt DC square wave, basically. And I've heard some rumors that this coil here, this common mode choke, it vibrates. So that's not good. You know, it's supposed to be sine wave here, but instead it pumps in a really harsh square wave. So, and the reason why it does that is to be able, as I can see it anyway, is to be able to drive that voltage doubler such that you get the proper voltages over here. A guy, Ilker, he has made a power supply for the C64C. Note that it's not working for the old one, or the one with large PCBs, only the short PCBs. It's because of voltage requirements of those ICs, like the VIC and the SID, that uses the analog voltages. And the thing is, it's so elegant. It has like a 5 volt 2 amperes generic USB charger, plugs into the mains, and then he has a USB cable with a DIN connector, and inside the DIN connector he has one IC and a couple of capacitors. So, and this arrangement is a voltage doubler. So now we have talked about voltage doubler. So basically what it does, he creates, with this thing, creates a 10 volt DC from the 5 volt. So you must also remember now that this 10 volt is now referenced to ground, not floating. And also it is not alternating, so the time of day will definitely not work. And he has also connected a lot of things there. So he has a cartridge, ST2 ESC, which not use the voltage doubler anyway, or any of the analog voltages, or 9 volt AC, and he has something in the user port. This is not the correct schematic anyway. So we need a schematic for the C64C, so let's see. You can see the power input, it's the same circuit as before. He has grounded this one, so you get the 10 volt DC in here, and then out here you get 9 volts from the diode drop. So you get 8 volts, 7 volts, and if this one is on, you will get 7 volts here also. I don't actually know, but I think this one doesn't have that drop at voltage, so probably you have 7 volt there. I'd like to ask Ilker sometime what you have there. If you see my video, please comment on that. So yeah, and also the voltage requirement for the SID is less, right? Because you have another chip. Same with the VIC. So, and then you have the cassette, which is driven by 9 volt unregulated. So I'm not sure if that will work actually, because this one will definitely need more than 100 milliamp. So maybe that's a downside. No. I asked Mr. Wilker if he wanted to look at 555 timer instead, because the reason why I asked him about this, because for first of all, I think maybe does it work? Is it possible? Because also the max chip is maybe not that easy to get. Maybe I'm wrong. And the other thing, if you want to make many of these, then it's better to have a cheap solution, perhaps a more powerful one. So basically what it does, it has a astable setting. It means that this output here is going on and off at a set frequency. And inside the chip there's a like a pull-up, pull-down configuration, like here. I looked at the data sheets. This one can provide 200 milliamps, and the max chip can provide only 100. And if you want even more current, you can do something like this. You can have your own transistors on the outside. So then maybe you have enough power to drive the cassette port. So that's something to think about. Maybe do a video on that on the breadboard. Because I have a 556 timer. It's the same, but it's 2 in 1 package. So could be fun. Yeah, so what's next? Of course you can get the Ray Carson custom Commodore 64 power supply. It has a 9 volt AC transformer in there. So it's a linear power supply also. So that will be very the same as the original. And what I wanted to talk about was the Jim Brain design. He got help from Bill Hurd. You can see that we have a like a square wave with a high frequency which is generating a sine wave. So that's the idea. So they use a high frequency transformer, which is the modern way of making power supply. So yeah, so this was at ECCC 2014, so I wonder what's going on, guys. Alright, so let's talk a little bit about the simulation I have done. Thought you may be interested in that. It's basically the Commodore supply inside the Commodore 64 actually, not the power supply. So this is the 9 volt AC, which I set 30 volt there. It's actually 50 Hertz. It's actually more like 12 volt amplitude, but that's okay. I have a 5 volt supply also, reference to ground. And I have no ground on this, so you have the rectifier that we looked at. So I haven't bothered taking these things. This only apply when there's high frequency noise. And these capacitor also. So for low frequencies like 50 Hertz, that won't make any difference. So, and this is the voltage doubler arrangement. And this is the 9 volt unregulated. So, and here you have the time of day generator. I couldn't find the Zener diode, which clips the voltage, prevents it from going too high and making this one latch up. That's a problem you have with the ICs if they get higher voltage on the input than what the supply voltage is. So I used for regular diodes to get approximate values. So basically they are clamping, and I can show you that now. So if I look at this trace, which goes in here, looks like this. It's about 12 volts. And as I said in the beginning, why isn't it 13 volts when it's 13 volts amplitude? Well, this voltage isn't reference to ground, so it's reference to ground via one diode drop. So therefore it's not 13, it's 12. Yeah. Just a little thing to notice there. A little nuance. So yeah, now if we look at let's zoom in a little bit. Like this. Yep. And now let's have a look here. We are looking here now, so let's look here. You can see the clamping going on at around 2.7 volts. It's not perfectly flat, but that's okay. So, and here you can also see what's going on in the output. Boom, it goes up to 5 volt, and on the way down it goes the other way. So basically, if I just look at this here now, and instead of measuring in reference to ground, I will measure over the input so you can see the input there. Yeah, I think you have to ignore that these are used as inputs. There should have been 5 volt then, if that was the case. But this is 2 input gate. So this LT-Spice program is not really good at digital design. So, but we have a 2 input AND gate. Then we have some positive feedback, and what the positive feedback does creates a hysteresis. So we have talked about that before also. And if you only look at the input of the gate and then the output, you will see how that works. So when, okay, actually we are measuring this one, so the thing is, for this output to go high, we need to pass 2 volts on the input, which is here. So you can see that around 2 volts something changes here, starts to change. And why does it jump? Well, that is because we have the positive feedback here. So when the output changes, so will also the input will be sort of dragged away from this. It's a reference. And the reason for that is because this is a slow moving signal and you want a sharp and no noise. If there's noise here, you will get some extra pulses, and you can count the wrong time because this is one time pulse, right? So you don't want some errors going on. So you have the output will help this one go over the top. And now that the output is high, the same thing goes when this is going down again. The output has to pass 2 volt as usual, and then it's held down, but the output goes down also. So yeah. Now, what happens if we introduce a power supply which is referenced to ground? Everything changes, right? So let's run it again, see what happens. Let's zoom in. You can see there's some difference there already. You can see that the voltages are now, because they are referenced to ground, you can see this one, which is here, it's no longer stopping at around 0 volts, because there's no rectifier diode doing that anymore. So the lead will now make the voltage go down. So, but anyway, this is not what he's doing. So, already through computer supply. So if I if I change this one to pulse, and the voltage is 0 and 12 volts. It's never negative. And it goes from 0 to 12, and the on time is 10 milliseconds and the period is 20. Okay, so let's see what happens then. And I put the ground here because now we know, because of this drawing here, we know that he puts ground here. And we also know that the power supply is actually referenced to ground, so this will also be referenced to ground now. Therefore I put a ground here. So it looks like this. It's a 12 volt square wave. It's a little bit less squarey at the beginning, because at the beginning we have some charging going on here. If you look at the current going on in the beginning there. But anyway, what happens here then? It's actually working, so I wonder why it says it doesn't work. That